All right, SI units, or as my boss at NIST used to say, God's own units. That was sarcastic. It was a little bit of an issue. All of our papers had to be written in terms of SI units because we work for the National Institute of Standards and Technology. However, in the particular field that we were in, nobody but Europeans used SI units, and even Europeans that worked in industry didn't use SI units. So, we were always converting from Teslas to Gauss. That's easy. Ørsted to amps per meter. That's hard, and so forth and so on. So, SI units, they aren't all that great, as we talked about in the previous situation. The reason why we like SI units for science is they're easy to deal with mathematically. They're easy to deal with mathematically. It's the same reason why Britain went to decimal currency. I don't remember exactly when, because I probably wasn't born then. If I was, I wasn't doing any currency trading. Basically because it's easier for computers to use decimals than to use really weird fractions. But, the old system was much cooler, right, in England. The old money. Now it's boring, right? But it used to be cool. The decimalization is important for science because of how easy it is to work with and to get exact calculations. Whereas the different units people used to use were easier because, they'd made particular choices based on the different kinds of work they did with the different units. So remember, a span is 5 L's, right? If you're working in those units, if those are the things that you're working with every day, then that's actually easier than wandering around with different with fractions, well, not fractions, but decimals and stuff like that. But when you get into more scientific things, then you want the precision that comes with the decimalization. And that's where SI units become very, very useful. They're not the only decimalized unit system, but they're the one that, it is the one that is used, and it's common, so that's what we should sort of get around in our heads most of the time. So SI units, that's what we use in science. We'll use them a lot in the class. They make life easier because you don't have to remember conversion constants unless you've been using those conversion constants your entire life, in which case, 12 inches in a foot, 3 feet in a yard, all that stuff. Okay, so SI units, we're going to look at, for most of the class, we're just going to look at mechanics. So there are 3 SI units for that. One is the kilogram, which is a unit of mass. Another one is the meter, which is the unit of length. The other one is the second, which is a unit of time. So imperial units, these would be feet, or no, these would be technically slugs, but we could also use pounds of mass. For meters, for length, that's feet, and time is seconds. And we can make combinations of these for what are called named units. So these are the base units. So we'll, again, eventually have something called a Newton, right, which is the force measure. Whereas for SI units, whereas for imperial units, that would be the pound. lbf, pounds of force. We won't have to worry about that conversion. If we get to the point where it matters whether you're using slugs or pounds of mass, I'll only do things with SI units for you. If you were engineers, maybe I'd do something differently, but for you, we'll only use SI units wherever there could be confusion between mass units. All right, which basically means in the next unit we're going to stop seeing feet and we're going to start seeing meters exclusively, because as soon as we get to forces, that's where we get these confusions. So try to get used to the SI units while we're doing it mixed, so that when we're doing it SI only, you'll be okay with that. So now the question is for each one of these, how big are they? Well, this shows us here. I mean, 1 kilogram is about the weight of 1 pineapple. Or if you don't have any pineapples handy, we are in Texas. I know I have a grapefruit tree in my backyard. 2 grapefruits is about 1 pound, or 1 kilogram. Meters, it's about the size of a countertop, about the size of one of those high tables at a bar or at a Starbucks or something like that. That's about 1 meter tall. It's a little above your waist, maybe around your navel. And then, so let's just write countertop. And then to get a feel of seconds, seconds is about 1 heartbeat. Obviously, your heartbeat varies per day or at different times of the day. Let's see. My Fitbit says I'm at 75 right now. Actually, something weird is happening. I should look at that. But so yeah, so it's not exactly 60 beats per second, but for most people, they want your target for your resting heartbeat to be around 60 beats per minute. Okay, so that's the sort of size, the approximate size of each one of these things. A kilogram is about the weight of a pineapple. Your countertop is about 1 meter tall, and your heartbeat's about 60 times per second or per minute. So that means that's about 1 beat per second. Kilograms were originally defined by water. And this was actually up until about 2019. There were little tweaks based on, the advance of scientific understanding of, the water phase diagram and things like that. But it was originally 1,000 cubic centimeters of water at 4 degrees C, because that's where water is its least dense. I guess that's the triple point of water eventually. Very soon after that, the triple point of water. Now it's defined in some complicated way in terms of the Planck constant. So there was a, up until very recently, they were trying to make a real standard, that is a physical standard, based off of silicon. So they made a giant, they may have made a couple of these, silicon sphere. I shouldn't say giant, it's 1 kilogram, so you can get this sort of idea about that. That was, grown very, very slowly over time to be a perfect sphere. And that was one candidate for the new kilogram, because they wanted to get out of this. I'm not sure why. This is probably one of the very best standards we've had. If the standard is, could we talk to somebody out in the middle of nowhere and tell them how we're weighing things? Here, in 2019, we decided, to go with something based on fundamental constants that we know about. And in this case, we use the Planck constant in quantum mechanics. That's the quantum of angular momentum, and it's sort of meaningless to somebody who doesn't have a lot of background in physics, but it's something that, if you're an alien and we broadcast, our weights and measures in terms of this constant, they should be able to figure that out. And if they can't figure it out yet, they will be able to figure it out pretty soon by the time they're able to receive broadcasts from Earth. How about meters? A meter is originally 1/40,000th or 40 millionth of the Earth's radius. And that was actually along the, I think meridian. Along the meridian that passes through Paris, because, the SI units are a French plot. And so this was nice and handy if you ever needed to know how big a meter was. You just pull the Earth out of your pocket, cut it up into 40 million slices, and you'd be able to measure something in terms of a meter. Now, at least, and this has been basically most of my life and all of yours, we've defined it as the distance traveled by light in 1/299 millionths, 792,458th of a second. It's small, but that means that the speed of light is, in the SI units, an exact number. There's nothing past 0.000. It's all zeros from then on out. So if somebody measures the speed of light and says that it's a little bit different from what we think it is now, the speed of light doesn't change, the meter changes. Which makes a little bit of sense, because the speed of light doesn't change. Our representation of the world should change by our knowledge of things that are really fundamental in the universe, right? Like the speed of light, not vice versa. So that's the situation there. So that's the way it is. So now we've got two things in terms of fundamental constants. What's next? The second. Originally, it was just 144,000th of a day. Pretty good. In 1983, at about the same time, they changed this to, looks like 9,192,631,770 periods of radiation corresponding to the transition between two of the hyperfine levels of the ground state of cesium-133. Again, not really useful for most people, but this is pretty good. Now, this is not, it's pretty good. It is not on the order of these guys. These guys are saying we've got something fundamental about the universe. We're using that as our standard. This is not using something fundamental about the universe as our standard. It's using a particular aspect of the universe, which makes it more like this definition of a second that comes from 500 years ago than like these guys here. So it's more of a medieval sort of idea, like these guys. This guy would have probably, looking at that's a little more precise. But these guys are less scientific in some way. I mean, it doesn't matter too terribly much, but that means if you have an idea about what you want to do to make this in terms of your fundamental constants, I guess you're the next up, right? So if you can figure that out, call the standard guys, wherever they are, in Paris or Geneva, wherever, I think Paris, and tell them your idea. And that's it. So that's your SI units. Kilograms are pineapples. Meters are high Starbucks tables. Seconds are heartbeats. All right, we will talk about this more next time when we're going to talk about conversions and what conversions actually mean. All right, bye now.